Hello, Jagdish, am I audible?
Yeah, Kiran.
Okay. So you'll see I'm making you presenter. Let me check once. Just
Sorry.
share, yeah, just share something. We'll see
Okay.
if it is okay.
Okay. Okay.
Yeah, yeah, it's visible.
Okay. Thank you.
Okay. Can you stop your sharing after just 5 minutes? We'll start. Okay.
Okay, fine.
Yeah, just 5 minutes.
Jagdish sir, welcome for the session, sir. Good afternoon, sir.
Yeah. Good afternoon.
Sir, within a couple of minutes, we'll start the session, sir.
Okay. Thank you.
Thank you. Good afternoon, one and all. Welcome back for the fourth day afternoon session. I am Krishnaveni, Assistant Professor from Department of ECS, KLEF. Feel proud to invite you for the afternoon session program on recent trends in embedded systems and IoT. For the afternoon session, we do have the resource person, Mr. Jagadish Verma. His education background: completed his undergraduation in electronics and instrumentation in the year 2006 from JNTU University, and completed the post-graduation in digital systems and computer electronics from JNTU University. He had a good industrial experience of 14 years in device drivers, validation in AMD, in the fields of 3D graphics, multimedia, set-top box, and machine learning based on Microsoft Direct ML APIs. Sir, we warmly welcome you, sir, for today's session.
Okay, thank you for the invite, and I want to thanks for this one KL University for providing me this opportunity to share some of the content, and especially on from the GPU embedded devices in based on the GPUs actually. So wait a second, let me share my.
Just now you got the privileges to share your screen.
Yeah, I got it.
You're perfectly audible, no problem.
Can you see my screen?
Yeah, it is visible, sir.
Okay, thank you. Okay, so today talk is like from my side. Actually, I'm going to give an overview of a GPU and driver validation. GPUs are basically part of embedded devices and which needs an device drivers for hardware interaction. And finally, like I'll give you some of the insights, like how to validate a graphics driver for some of the use cases. Okay. Yeah. Okay, so before I start this session, I just want to understand. Do we have? I mean, anyone knows about the GPUs and what are their use cases? How they use? Okay, no problem. So yeah, of course, I too don't know before I joined in AMD, since I have been working here for for 14 years on the same thing. Before when I was in a graduation, I too don't know about the graphics. GPUs are useful for useful as embedded devices. Okay, so before I go into actual topic GPU overview, so I want to tell about what is a CPU first and what is the difference between the CPU and GPUs. So basically, okay, yeah, CPU is central processing unit, which is a heart of the any PC, and the CPU basically does the basically does the wide variety of the applications. Like it is kind of like a general processor. So that means CPUs can be run in multiple applications on a system, which varies a range of the complexities. Okay, and the next one is like the CPUs are the is a task manager. Task manager, in a sense, like this is a basic thing which can schedule jobs, and if we on a system we have multiple processors are there, and the CPUs are basically schedules a job which one has to run by the processor. And the next one is it's a versatile device, performs a various series of tasks requiring a lot of interactivity from the user. Basically, this means when the user is running some applications, actually the CPUs are actually devices which have a more interactive with the user. Examples, a file copy are running the different complexity of the application. And on the right side, if I go into the in details of the CPU, inside of the CPU, this is basically on the right side, you have the block diagram, which has insides of the CPU hardware blocks are there. Okay, basically a CPU consists of a processor, ranges from the single processor to multiple processors. Nowadays, we have CPUs we have CPUs with the 64 core and 32 cores, and even higher amount of the CPUs are also there. This is an example for an CPU processor which contains 4 processors. Like on a red block, you can see on the top, there is a red blocks are there. These 1, 2, and 3, 4. These are like a 4 CPU cores in this single die, a single processor chip. And each processor has arithmetical logical units and registers. These are the basic things which performs computational work for us. And each CPU, each processor can run a single application. So that means in a single application independently. Like means if we have a multiple processor, multiple cores on a CPU, so that means we can run a multiple application parallelly. Providing the application has the provision to use these these CPUs, like leverage the CPUs by coding should be there. So that means a single processor. So if we have number of the cores, if we can run, my program is capable to run multiple, can leverage the multiple processors. So that means we can double the output, than the single processor. So likewise, so on. And after that, the next block is the bottom one is, sorry. Okay, so next part of the block is like a cache memory, which is like a L1 and L2 here, and the another memory is like a L3. L1 and L2 are dedicated to each core, and L3 is a common for all these processors. L1, these caches are mainly basically to store instructions or data which needs a frequently executed by the CPU, these cores. So that means the CPUs can access this cache memory faster than the main memory. Main memory in the sense of like our external RAM memory. This cache memory is accessible faster than the main memory. And one thing, like if the application, if the cache memory is not enough to run the application, then it takes from the main memory, copies the data from and to between the cache and the main memory. And apart of this cache memory, we have 2 controllers are there. One is a main memory controller, and the other one is a graphic controller. The purpose of the memory controller is basically to interact with our system RAM or main memory, which is a DRAM. So basically, this connection between the memory controller and the external RAM is established through a bus called as a memory bus. And then coming back to this one, graphic controller, there is this graphic controller connects to an external GPUs, which are connected through an PCI Express, which is like a high-speed bus. So usually the graphic cards are used to be inserted into the PCI Express slots. Okay, this is a basic view of the CPU and the CPU inside view of the CPU. And coming to the GPU, GPU stands for General Graphic Processing Unit, which performs like a specifically graphic intensive kind of applications. But nowadays these are more famous for using in a machine learning task. And basically the GPUs are contracts to the CPUs. So the CPUs are basically, I said, it is used for general purpose of the computing, whereas the GPUs can be used for repetitive kind of calculations. Example, any mathematical kind of calculations can be done using a GPU, but the thing is GPUs are specifically designed for few operations, whereas the CPU can designed for general purpose computing. And on the right side, we have basic PCB view, I mean, printed circuit board of a graphic card. In a graphic card, we have this red color highlighted, or basically the like a RAM memory. The RAM memory card also has a dedicated memory. And these memories are like in a ranging nowadays. The graphic RAMs are ranging from 8 GB to 10 GB of memory, dedicated memory it has, so that the graphic card can save the data directly into this RAM instead of the main memory, so to reduce the processing time. And apart from the RAM, we have a main block in this printed circuit board is this one, the largest square, which is a GPU. So this is the actual heart of this PCB. And the down we have like a gold-plated pins are there. So usually we have to connect these a graphic card to the system onto the PCI slot, PCI bus through this connector. Yeah, next one. So this is a basic view, inside view of the GPU. Like CPU, CPU has the cores the same way we have cores in a GPU, but the cores in a GPUs, unlike the CPUs, the cores in the GPUs are like 100 to 1000 now. So recent days, it is something like 100 to 1000 number of the cores are integrated into these GPUs. So this is a basic view of that GPU. So considering every cell here in a grid has like a one processor in a GPU. So likewise, we have, this is a typical illustration for 100 GPU cores. And it has one thing is it is basically, it takes one instruction and performs the operation on different types of data for the same instruction. So each core performs works on different data, but for the same instruction. And it has this one, like it is again splitted into clusters kind of thing. So let's say we have on top, we have red color. These are the red colors are signifies the clusters. Clusters in the sense like this, each row is they segregated into a cluster. So we have each red color represents the cluster for that specific core. So when the graphic card is executing, a graphic processor is executing some instruction, one instruction, on different data types. If one cluster is completed its calculations, and it can be ready for another instructions of the GPU. So this is that. So basically, this we can say, like I said the single it execute a single instruction on a multiple data. So that we call as a single instruction multiple data, and a short we call as a SIMD. Yeah, this is just a like a comparison or summary of the GPU versus CPU. What is the difference between the CPU and GPU? CPU is basically the central processing unit, and the GPUs are graphic processing unit. And the CPUs, we have several cores are there, like a limited cores are there. Usually it's like an tens. Earlier we have like a 2 cores. Nowadays these are coming around 16 cores for general purpose computers. And whereas in GPUs we have 100 many cores, which is like as I said, is 100 to thousands of cores are there in a single processor. And CPUs are basically for low latency kind of applications, low latency of the applications kind of thing. Or usually these are like user interaction kind of applications that the CPUs are targeted for. And whereas the GPUs are like a high throughput in the sense like the in a parallel how much the data it is computing on a single unit. So basically the GPUs are provides like a high throughput. And whereas the next one is CPUs are usually good for serial processing. This is because earlier we have single, though we have multiple cores on a CPU, but usually the earlier the programming applications are not leveraged to those multiple cores. So on a single core itself, it is the application being multiple applications being executed serially. And whereas the GPUs are like, since it has a multiple processors, and at a time it can execute the data. So these are GPUs are good for parallel processing. And finally, the CPUs can do handful of operations at once, and these GPUs can do thousands of operations at once. Thousands of operations means, since this depends upon again the number of the cores are present. Since the GPUs are more cores, so it can provide thousands of operations than compared to the CPU. So on the right side, we have, this is just, I have given like illustration, like how the GPU or the CPU on real time looks like. This is a CPU processor, which is actually based on AMD, AMD based. And the next, like this is the GPU card, and it's it looks like this. And inside this fan, under this fan and heat sinks, the printed circuit board, on top of the printed circuit board, the GPU is present. The next one is like a GPU solutions. So I said that GPUs can be useful for parallel computing. And what are the real applications of a GPU, where the GPUs are really using in real time? One is the first one is a 3D gaming. 3D gaming is basically nowadays the 3D games are more realistic kind of thing, like more realistic and also are running at a speed of even 200 or 300 frames per second. So unlike the CPUs are basically, we can't get that many frame output on a CPU. Usually the CPUs are can produce per second 10 to 20 frames, but for gamings are really more key on a gaming. The more key is like a speed, how fast the number of the frames are changing on the screen. That is a factor. So GPUs are basically our main usage in a 3D gaming. And the next one is this content creation. Content creation is basically in a movies and kind of thing. We have a large landscape kind of graphics will be there. Like a example, this case is like I have taken a screenshot of this Bahubali movie where we have this the Empire King, this one kingdom is kind of to represent that that graphics at on a single on a single on a second. So that requires a lot of that needs a lot of compute power, and the GPUs are basically can do these kind of jobs. And not only the movies and films, and we have usually we use GPUs for content creation for multimedia kind of applications. Multimedia content kind of the video editing kind of thing. So underneath we graphic card has a multimedia hardware blocks, so it can provide the video encoding and decoding on like 4K and 8K kind of resolutions. And then the usage of the GPUs are machine learning and cloud computing. So the first one is like a cloud computing application where usually the cloud computing is something like on a remote, on a service provider, they have a server system, and it has a high power, high performance GPU card will be there. On the other side, the end users like the game players can connect to that server in a virtual session over the internet with over the internet device, like any device in the sense ranging from the mobile phones to laptops or tabs. We can connect to directly to that server through internet. And so even if your laptops or mobile phones are not capable, are low-end processor, low-end devices, it's okay. But the only thing is like the rest of the jobs are the actual application is running on a server side into multiple number of the sessions. So in this area, basically, we have two things I want to highlight. One is like encoding part and decoding part. Encoding is something like when the game is running on a server side, that data will be compressed into the codec formats, and that will be broadcasted, transmitted over the internet lines. On a receiver side, are end users who runs the game that has a decoder logic, and so where these applications the data will be decoded and displayed into your personal devices. So the main goal of this one is like, even though you have low-end devices, the target is like the minimum 60 FPS of gameplay on a remote. So this is something kind of a machine learning and cloud computing kind of the servers which use there. And the next one is like a research and science applications. So this is basically the biosciences where we use a large number of the data research purpose. They use a large number of the data and then finding some drugs and predicting the possible output in a faster way. So in those cases, the machine learning will be used, and also again the GPUs are produce much faster output there. And then next one is data centers. Data centers are basically these are server kind of computers which have which are capable of machine learning. Machine learning hardware is also will be embedded into this servers. And finally, the automotive cars. Automotive cars is is a recent technology. So these are like one-way automotive cars are self-driving cars. So the cars can be driven self based on this one, based on path of the road, and the object detection and those kind of things will be taken care by processing image detection, or the signals and those kind of things will be detected by the machine learning and processed by the GPUs. Altogether, I just shown what of discussed about what are the uses of use cases of the GPUs, and in reality, like how it looks like. I just want to give present a short video so that you can see what is what are the. Okay, that is a cool, the best video I have. I want to just I want to show all the whatever I discussed, the GPUs use cases, like ranging from the cloud to gaming consoles or gaming or virtual reality. Everything was shown in the presented in that video. So I'm going to the next one. Yeah. Next one is like a GPU hardware blocks. This is basically from the AMD hardware, AMD graphic hardware, which is the recent architecture, the RDNA architecture. You need not worry about much is this architecture. What this architecture means? This is an advanced architecture, internally they call. And on the right side is a typical. This is a typical GPU. Typical GPU inside. These are the number of the hardware blocks is present. These are the number of the hardware blocks are present. The main hardware block is basically the GPUs are for a gaming purpose. Essentially, usually primarily for a gaming purpose. Gaming are the real and 3D content. So this is a geometry on a middle. You can see this. There is a block called as a geometry processor. This basically this geometry processor. What this block does, it usually the 3D content, everything is present in 3D coordinates format. When we run any 3D application or 3D video, So that initially it will be in a 3D coordinates file format, and that is converted into a that is converted into a 3D kind of objects and present into a screen which we see on a display. This is that is a primary purpose of this geometry processor. And next one is a graphics command processor. Basically, this command processor takes the a number of the instructions from the application, and it execute one by one here. Okay, and this is one way I can say like a command processor and the scheduler kind of a job it does. And the next main block of the main hardware block in these GPUs are shader engine or compute cores. These are like on a red color, we have like 4 cores are there in a quadrant format. And each core, each quadrant each block again has a 5 number of the cores, compute units are there. So that means actually total in this block we have 20, and each compute unit has internally it has 2 compute units. So total, this is like a earlier couple of years back hardware GPU block which has like a 40 compute units or 40 command processors. And so the main purpose of this thing is, like I said, SIMD means like it takes a single instruction and execute a multiple data and multiple data in parallel. So those mathematical operations will be performed under using this hardware block, compute hardware block. Or and again, one more application is like something like some mathematical calculations, vector-based, or especially for 3D applications, rendering, calculating the real-time data like shadows and those kind of things in the game that will be calculated here. And the next block, another block is major block is multimedia block, multimedia engine, which is which does the encoding and decoding part under here. When we play any video or play any video through our video players like movies and TVs or VLC or something, or YouTube, online streaming content like YouTube, those content will be processed by this multimedia engine. And apart from this, as said, we have like a dedicated cache memories there. So this is each block contains a dedicated cache memory. So this cache memory stores the repetitive instructions in cache, and also like a dedicated another cache is like L2 cache. The overall, the outer line we have is like we have a 64-bit memory controller. This memory controller basically to interface between main memory and GPU memory via through this memory bus. So this is basically typical hardware blocks contained in GPU. So major ones are major in a compute, basically machine learning, those kind of the operations. So these compute engines are the key main hardware blocks. Okay, so we have so far we have I introduced the GPU and hardware part, and what is about the software part. So basically, for GPUs we have GPUs also needed a device drivers for doing this interacting with the hardware. So what is a device driver? A device driver is typically, this one is simply like an interface between the user applications and the hardware. hardware is here in this case is GPU hardware. So when I have any application, kind of a 3D application or machine learning application or anything, that when the application runs, that application will trigger the driver, the device driver, and then for that application, the developers usually allocate some memory and send commands to the hardware to the processing those data. And next one is like a graphics driver. I said it's a device driver, and in a graphics driver code, usually the graphic driver code is split into multiple modules. Unlike like any other software, graphics driver is also split into multiple modules. In each module, serves the specific use case. Here an example. When we compile a graphics driver, that means when we compile a graphics driver, it will be created into multiple object executable files kind of thing. So here the use case is something like there is an executable file, separate dedicated executable file will be there for each use case. Here the use cases are something like gaming and multimedia and machine learning. These are the use cases or applications of GPUs and display modules. These are some of the examples of the modules present in a graphics driver. So, and again, each module can be categorized into two types. One is like a user mode, and the other one is a kernel mode. User mode is something most of the driver modules in a GPU graphics driver are user mode drivers, user mode modules, and the only there is a few modules are there which is related to kernel related operations. So those modules only are kernel mode drivers. And apart from that, the rest of the driver modules are user mode drivers. What is the difference between the user mode and kernel mode is when we run any application, this application will be primarily sits into allocate a memory in space in main memory, which is a system RAM. And so if we have multiple applications or 2 to 3 applications, it has a dedicated memory allocation in a system memory. And if one application has accidentally violating due to a bad program, if the application is accessing the memory space of the next memory address of the next processor and next space of the memory of the another application, then at the time the beauty of this one is the only application will be crashed. Application will be crashed into then the rest of the applications will still run on the system. And whereas the kernel mode is something like the user mode has to send a system call. User mode driver has to send a interact with the kernel mode via system call. When the system call it triggers a system call, then it allocates some it will give an access to the hardware blocks, a kind of like GPU hardware memory and those kind of things. It will give an access to memory or those hardware resources. So if something is like when the driver is in kernel mode and if it is violating the then the entire OS will be crashed. So this is a typical difference between the user mode and kernel mode. And as I said, driver modules usually after compiling the driver source code, it will be generated into each module will be have dedicated executable file. Usually that we call as a it is in a format file format as a .dll. So this is basically these are like a dynamic link library kind of executable. So on runtime, the application time call on runtime to interact with these functions. And examples are AMD OpenCL.dll, which is a module which used for machine learning kind of applications using the OpenCL language. And whereas system kernel mode modules are the drivers are in format of .sys, because these are system files. So all kernel mode modules of the driver should be in are in a format of .sys files. Example, in AMD, we have a driver module called AMD.sys. And so far we have this one. I introduced this one graphics driver. What is a graphics driver? What is a modules kind of thing? So what is the language we have to use to write this GPU device driver is one. The main language we used in GPU device drivers are C++. For a high level of language. This is basically because of most of the 3D applications are most of the 3D applications, including the multimedia kind of players, will our users are write in a C++ language. So driver is also created in that, are programmed in a C++. And the next one is assembly language for low level of hardware blocks. So this is basically for shaders and compute engines. So these are these kind of to interact with this to interact with these hardware blocks. We have to write a code in assembly language. And next one is for machine learning kind of applications programming. We use OpenCL APIs. These are the APIs which use multi parallel kind of programming, parallel programming. And another one is a Cuda API. So Cuda is basically the NVIDIA machine learning API, and OpenCL is open standard from the AMD. And finally, graphic driver source code is an approximately 1 million of lines of code. This is a huge number of the code lines of the code for this for serving all these purposes. Okay, next one. So I just want to show this interaction between the application and the hardware, GPU hardware, in terms of driver communication. So this is an that architecture interaction, kind of architecture interaction between the application and driver, display driver, AMD device drivers and the hardware. In this, main thing is as we have two memory spaces. One is user mode driver and the kernel mode driver. So we have the kernel mode drivers are, in short, we call as a KMD. These are runs using kernel space. Whereas all rest of the drivers, rest of the modules of the device drivers uses user space of the RAM. So this is a typical typical hierarchy architecture kind of thing for 3D applications. Usually the 3D applications is something like for multimedia, we use this one, Maya, those kind of animation kind of applications. And one more is even multimedia players, the popular ones are like a Power DVD and movies and TVs and web, YouTube, and these kind of applications uses a 3D 3D APIs, which are, there are two types of 3D APIs. Again, I can say like there is for creating those applications, animation applications like Maya or Studio kind of applications, AutoCAD or something. They have to write a program in a 3D library API, which is there are two types of library APIs are there in a real-time market now. One is like a direct 3D. This is kind of a 3D API, which is from the Microsoft. This is a proprietary of the Microsoft. And one more is like OpenGL. So OpenGL is also an API where we can use these APIs to write a code, write an application, so like something like Maya and those kind of applications. So this is open standard, and this is one is like a Microsoft proprietary. And when any 3D applications like movies, any 3D applications like any like Maya and those kind of applications, when the application runs, first it will call main module kind of thing is called as a direct 3D runtime. This runtime is is from the Microsoft side. So it will first trigger call this runtime, 3D runtime, and then this runtime will like invoke command to send a command to the device driver, which is a user mode driver here. And then once the user mode driver is initiated, and then the user mode drivers sends signals to the kernel mode driver through, again, on a runtime, Microsoft runtime, to a kernel mode space. Here, the main block in kernel mode space is this DXG in a system file, which is basically this DirectX graphics system file. Which does the scheduling and memory manager kind of tasks. And once that was done, then it sends the commands to the kernel mode driver. Kernel mode driver basically allocates some memory required for running this application in a hardware. So basically, user mode driver can't can't access the hardware memory directly, so it has to go via kernel mode driver. Kernel mode driver allocates the memory for running the program on a hardware GPU. Here, the hardware is like a GPU hardware. And the next one is here the same way. Similar kind of 3D, we have OpenGL, and it has to send signals to, it will invoke OpenGL driver, and then it sends the commands to the kernel mode driver, and the kernel mode driver sends the commands to the hardware. So this is basically a interaction between an application through a driver and then hardware. Okay, the next topic is like a driver validation in a GPUs. So basically, the validation is like a standard statement, like a processing of the process of validating the software, whether it meets the exact needs of customer or not. So this is basic definition. So basically we do like as per the customer requirements or product requirements. The software is designed and software is working, we have to check that. And in that process, we have validation process involves activities like unit testing, and then interaction testing, and system testing, and user acceptance testing. And on the right side, right bottom, we have like on each level of testing phases are there. Kind of first it starts with the unit testing. So basically here, when a developer writes a code, implements a code for hardware functionality, for specific use cases like multimedia or those requirements, feature requirements, the developer writes a code, and then that being tested by the developer on his own, or he or she test on his own, and then it gives to there is a like one more initial test team will be there. So that test team does basic developer kind of a testing, or UTP, DTP or UTP kind of a testing. So they test all the functionalities of that feature with respect to that specific module only. Modules of drivers are like something like a gaming and multimedia. So the next one is once the driver is the developer code is fine, doesn't have any issues, and there are no issues with that, then the driver will be given to next level of testing team, is integration kind of testing. Basically, integration is something like we integrate multiple modules and make into a package. So with each module, we can't test each module separately. So we have to integrate all the modules and create a driver package. That driver integration team install, and they validates the basic sanity of all the modules, functionalities of the all the modules. So the primary difference is unit testing. This testing team focus only on specific functional module, and whereas integration testing does like across the modules, but on a functional sanity level. And the next phase is like a regression testing. Regression testing does something kind of like when a developer again when there is a bug. There is a bug, and the developer has fixed that bug, and this that will be given to via unit testing and integration testing, and finally to regression testing to validate it. And if there is some issue between them, between the previous driver to current driver, that will be validate here. And finally, the user acceptance testing, or customer end user kind of a testing. They will test the broad number of the hardware and the OS combinations and the applications, and so and finally, after their conformance, their quality assurance, finally the driver will be released into the market. So this is a typical flow of the testing levels in any industry, or like the same model will be used in graphics testing as well. And coming to the coverage wise, the test applications, what the test areas they do, like something like for validating the graphics driver, what are the testing it has to do? One is a certification testing. Certification testing is something one like here the certification is we have to certify our driver with the OS. Usually the majority of the driver, majority of the graphics driver, majority of the drivers are like is used in Windows. So basically Microsoft provides some provides a certification test with respect to that specific hardware. Here the case is like a GPU hardware. We have set up, they provide a specific set of the certification test. So once the certification test pass, then finally Microsoft signs. These driver is compatible with the Microsoft. That certification sign off will give. And the next one is functional testing. Functional testing, usually we validate the functionality of the driver. Let's say something like, if let's take example, for example, we have a multimedia players. The prime we run a video clip, but that video clip is really using the hardware, GPU hardware acceleration or not. That we have to confirm. Those kind of the things will be performed under functional testing. And performance testing, apart from the performance testing is a key again. So functional testing is provides the quality of the device driver, but performance testing is performance testing is one which gives the how is it performing? Is it producing the output or number of the frames as per the market or not? Like that kind of testing done here in a performance testing. And finally, the stability testing. It's a kind of endurance testing. So kind of let's say an example, the if we take into multimedia application into an example, kind of Amazon or these OTT applications. Usually users will watch some videos or movies or over the long time. So those kind of the stress cases they have to do in a stability testing will be covered. And finally, test engineers. So basic roles of a test engineer here is validate the driver, and then the next one is this is the validating the driver in terms of these coverages kind of thing. And the next one is finding the culprit change. If there is issues there, and previously that functionality was working, and someone has to identify from which developer change that issue was introduced. That we need to identify here in regression check. And the next one is like a debugging. Debugging means we have some in each functionality we can disable some of the code with the registry keys from the control panel. So that can be basically here they do disable play with different kind of settings, and finally identify from which part of the software it has introduced the bug. They will identify here in debugging case. Next one is testing multimedia functionality of the GPU driver. So multimedia, so this is an use case I have taken for this session. GPUs, how the multimedia functionality will be tested for of the GPU device driver. So basically, multimedia applications, we have two things. Basically, any application, one is an encoding part and the decoding part. Any application will multimedia application. These are the two things. One is like encoding. Encoding something. Encoding is a process of representing data in a different format. Actually this is kind of converting a raw data into a codec format. Raw data is like a YUV format, and that will be converted into a codec format into this formats, encoding formats. Codec formats, usually AMD supports these codec formats. H.264 and MPEG-2 and VP9, these are the codec formats it supports AMD driver. And the main functionalities are main use cases for this encoding are conferencing, we have in any conferencing is like any meetings, video. Video conferencing calls and those kind of things. There it uses encoding part. On live, it converts the raw, capture a video when the presenter is presenting, and that will be converted into codec format, and then cloud gaming and streaming videos live videos. So these are the areas where the encoding part is comes into the picture, and decoding part is the inverse of the encoding part, which is converting encoded data into a displayable format or a raw format. Usually the common use cases for this decoding is video playback, and even the games uses a decoding for some kind of a cutscenes kind of thing, promo kind of thing. And next one is multimedia use cases using the GPUs. These are typical use cases on a table I have kept here. Multimedia use cases, basically the video editing is a one. Video editing is a one which we edit the videos. User edits the videos on its own. The common areas involved are like a video decode format and encode format. Encoding again comes into the picture for compressing the video. For compressing a video as a particular requirement. And video conferencing, example, Zoom, MS Teams, and Skype. So if we have more number of the users, and the clarity and the one is like the handling the more number of the users, also limitations right now. So that will be, the more feature will be created using the hardware video conferencing. So the basic areas here are video encode or decode blocks will be used, and video playback. Video playback is we use on offline media players kind of thing. Movies and TVs is a Microsoft one, and Power DVD is again it's a video player, and here only decoding of the multimedia engine will be used, and the video quality enhancements will be there. And next one is like a video transcoding. Transcoding is one is like a live streaming kind of thing. Example, YouTube, we have live streaming, and Twitch. Twitch is also a kind of a live streaming tool they'll use. And here the encode and decode will be used. And finally, the OTT content, Amazon and Netflix, these applications will be used decoding format when some movies or TV applications will be program will be played. And the next one, the types of the bugs in multimedia testing. What are the types of bugs we generally we see when we test a multimedia when we face when we play multimedia applications? One is the main thing is we have to check the hardware acceleration is engaged or not. Hardware acceleration is both encoding and decoding. Encoding part will be used when we record any video, or decoding will be used when we play any video. So while doing that process, we have to check whether it's using the hardware blocks of the GPU or not. This is a primary basic check. and if not, that is also an bug. And next one is a screen issue, green screen or black screen during the playback. These are when we have problems when in playing a video from the due to the data loss from the decoder, when the decoder is unable to decode that compression video. So those cases, this green screen or black screen will be present when any video playback is happening. And one more is frame loss. Frame loss, you can see when we play any video, you see a frame loss kind of thing. In middle, you can see some stutter kind of thing, or these kind of things will be happen. That, I mean, there is no smoothness in the playback. That is basically due to the frame loss. And next one is black box kind of a corruption during the playback. You see some kind of a glitches and block kind of a video is not playing properly with some glitches kind of thing that you can see. And finally, the crash, when the application is unable to initialize due to a driver issues, those also will be, you can see a crash. Okay, so this is the part I want to present, and finally I have a demo to show how the real-time this multimedia applications are using in GPU, and how we have to validate our driver with respect to the videos. Let me share my let me connect it to my remote system. Actually, can someone help me how to switch to another window?
Sir? Sorry, sir.
Yeah, actually, I want to switch to another window. So how can someone help me on
Is
this?
the sharing content or from your desktop screen, sir?
Sharing content.
Sharing
Yeah,
content.
desktop. I need to change it to another window.
Okay, you try Alt Tab, sir.
Okay.
Alt Tab. No, sir.
Still, I think still it is presenting the PowerPoint presentation.
Stop
Okay.
your sharing, Jagdish.
Yes, sir.
Yeah.
Stop sharing and share the screen.
And now share it to whatever you want that screen.
Okay, thank you. Okay, so so this is my environment where I have I think you can see my screen, right?
Yes, sir.
Hello?
It is visible, sir. Yeah, sharing.
Okay. Okay. So so this is my my environment where we have that GPU is present and driver as installed. Here the test environment here is like on a Windows OS. and I have the GPU. Prerequisites are the system should have a graphic card should be there, and one more is like the driver is also installed to the respective hardware. So I have installed the driver already for demo purpose, and if you want to confirm it, go to right click, and here there is like an icon will be there, AMD Radeon Software Edition. So this is a confirmation where you confirmation for the driver is already present in your system. Okay, and so I'm ready with the system and with the driver installed. So I just want to show some of the applications, use cases. I discussed how the GPUs are using the using the hardware acceleration for the multimedia content. First one I have two. I'm showing this playback scenario where I have coded two different video clips are there. So this is offline content. So this is basically from MPEG to this is offline file. Okay, so I opened that with the multimedia content, video MPEG-2 content using the movies and TVs application, which is like a Microsoft player. And now I said in a previously when we play back, it should use encoding part of the GPU to show that there is a task manager. In task manager, we have like a performance tab will be there, and here tab is like a CPU utilization. We have one more section called as the GPU section is there. So in this okay, in this we have this one. Yeah. In this one, we have a category called as a this one video codec. So this is where here you see earlier when I stop a video, stop presenting a video, stop playing a video, that clock frequency is going 0% of utilization. Hardware decoding is not used here. It's going to 0. And when I play the video content, it start using this acceleration. You can see the bump in the utilization. So that means it is using the video decoding engine of the hardware, GPU hardware. And the next example I want to show, next use case I want to show is our traditional YouTube content. Okay. Here, when the media is like a content is playing on this player, you can see again the codec part. It is utilizing this GPU hardware. There is a bump in spike in this one. So this represents it is using the video decode format, video decoder of the hardware. If I start playing this, it will be unengaged. Okay, yeah. And one more thing is we have to see here is there is an option. If you right click it, it will give the codec information. What are the content it is used? Like here, it is using this file is like with the VP09 codec. And if there is any the particular resolutions of the statistics like a video resolution and how many frames it is rendering at, that gives information here. If there is any loss in the frame, that also here mentioned here gives that stats here. And the final thing is like I want to give this one encoding part. Encoding part, I have a tool for capturing, which is again okay. So I'm just capturing desktop here. I'm recording a video so that it is like a simulation of what we have in this one, the real-time video conference. So okay, it is already started recording. Recording is in progress. Now I need to check this one. Yeah. So this is an encoder part. So it is leveraging this one, engaging the GPU hardware. When I stop it, it should stop using this one. So it is, yeah. Yeah, now it is like there is no. This means that the deadline means there is no usage of the encoding section. So these are the typical use cases of GPU hardware, and what usually will be verified when we have like a device driver validation for multimedia applications. So yeah. Uh, okay. Yeah, I'm done with the demo and my presentation. Do you have any questions? Hello?
So, what is the difference between GPUs and CUDA, CUDA architectures?
Sorry, can you repeat a question, please?
So, what is the difference between GPU and CUDA?
Okay, so basically, GPUs and CUDA. GPUs are anyway, like GPUs are general purposing compute general purpose units, and inside that GPUs we have like a hardware blocks. I told let me show into. Let me go back to my previous slides. Okay, so yeah, this is a diagram. I mean, inside the blocks of hardware blocks inside the GPU, and in AMD we have compute units, right? So these are basically for mathematical applications or machine learning applications, machine learning. Computing calculations, these will be used, these are compute units. Like the similar way, NVIDIA has NVIDIA, they will call as those compute units as CUDA blocks. So GPU and AMD, the term is compute units, and NVIDIA CUDA is basically for CUDA is hardware block, the compute blocks in NVIDIA. Is that answer your question?
So, coming to the computing perspective, is it these two are different, right?
Yeah. Computing perspective means CUDA, and are you talking about CUDA and compute?
Yes.
Okay, so compute point of view, both are the blocks are similar. Blocks are the functionality wise is similar. Functionality is same. Basic functionality is same. CUDA performs the calculations, computing calculations for machine learning, whereas in AMD, those compute units, those hardware blocks are named as a compute units. So basic purpose is same. Both purpose is same for machine learning applications. In AMD uses compute units, whereas NVIDIA, there is a graphic card from NVIDIA. They use they will call as those blocks as a CUDA blocks.
Yeah, participants, if you have any doubts,
Yeah, if you have any silly question, also you can ask me. I can help you to. I can help you to understand your.
Sir, I am Krishna Veni, sir, from Department of PCS. Sir, I have a small question. For example, if we are in a plan to design one prototype embedded platform, that too for a dedicated specific application, for example, health monitoring kind of a platform, if we would like to create, then we have to give the architecture from the kernel level as well as the device level, sir.
Yeah, correct.
So for that, is there any specific kind of the existing architectures are there, or we have to start from the scratch, sir?
Okay, for medical applications, right?
Yeah.
Medical applications from kernel level to this one, right? Your interest is like from kernel level to the design phase, like hardware, including hardware.
Yes, sir. Yes, sir. Kind of a prototype, like proprietary platform, instead of not like existing platforms what we are using.
Okay,
How
yeah.
design?
Okay, so to answer that, basically, these are like customized hardware. Usually, any embedded hardware is like a customized as per the use case. So basically, that is an embedded device since embedded device is targeted for a specific application.
Yes.
So every hardware has any hardware for any functionality, like your medical application or for any other application. It will be customized as per the requirement. For general purpose, actually, most of the applications, embedded applications, in embedded cases, most of the things ARM processors are used. Basically, those ARM processors are like a simple kind of application, simple kind of a processors. From that, they will customize as per the hardware SOC. These hardware developers will ask for customization based on the need. So ARM processors are general purpose. So it solves the process, solves any requirement. Is it answer your question?
Yes, sir. And I have a little confusion about we need to concentrate to customize the kernel architecture or the device architecture, sir.
Device architecture. Kernel is like kernel is based on again our hardware. So kernel is a software side, and hardware we have to customize it. Kernel you can do we can modify or we can modify the program, but hardware level the main challenge is from the hardware side, the customizations.
Okay, and that too, it affects the device drivers while we are making the configuration process and all. And according to the requirement, we are supposed to install the particular device drivers. Am I true, sir?
Right, correct. So, so once we have finalized this one, the hardware, we have this one like a kernel side. Kernel side can be customized actually. Kernels also in a Linux OS, we have a custom. We can have the OS, and that can be customized as per our requirement for our device. Hardware thing, the main challenge is when we have to have a proprietary, the first phase should be the customization in terms of we have to select the processor first, processor first, whether it's meeting our requirement.
Yes, sir. And to build such kind of a customized hardware, like at the device level, kind of any laboratories are existing, like in educational institutions, like we don't have the customization and laboratories to get reconfigured and to see the results, etc. Sir, is there any suggestible platforms are available, sir?
Actually, this customization, I can't give an exact answer for it, but actually we have we have customizations in a processor kind of one is ARM processor, one more is like a Raspberry Pi. So these are the basic customizable. So these are the processors are using across the like a wide variety of applications.
Yes, sir. So once if we decided to go at the device level kind of a customization, definitely we need to approach the industry, right, sir?
Yeah, correct.
Yeah. Thank you, sir. Thank you very much.
Thank you.
So will you suggest any kind of open source platforms to get more knowledge towards the development or to get the good kind of something like that?
Okay, open source. Actually, I need to look into it. Actually, I didn't work much on that area. I didn't get a chance to work on that.
Yeah. Sure, sir. Thank you, sir.
Okay.
I request the participants, anyone would like to interact, you can please. Yeah. Thanking you very much, Jagdish sir, towards the CPU and GPU and its architectures and the device level modeling and how it go with the kernel level and the software things, particularly in testing part, what are the stages it's required for a perfect hardware to get in the final development and etc. And really, it's a wonderful session, sir. We really feel that this is how the process flow has happened in AMD and how it is actually, this knowledge is actually required to go for the next kind of knowledge and all. Thanking you very much for your valuable session, sir. I request participants, please be in touch with the WhatsApp group. So the feedback link is shared in that group. Thanking you very much.
Okay, thank you. Again, actually, I'm thankful for this opportunity. So one way, actually, this is my first lecture. Thanks for giving me this opportunity. And so this allow me to share some of the thoughts from the industry.
Yes, sir. Thanking you. Thank you so much, sir.
Okay, thank you.